7, 6, 5, 4, 3, 2, 1. And we're live. Let's do it. This is Retraice for November 25th, 2022, a Friday. It's segment number 61. It's 11 p.m., 8 p.m. Pacific. We're going to talk about formal languages and pseudocode in the context of the Appendix B in AIMA4e, Artificial Intelligence, a Modern Approach by Russell and Norvig. What is Retraice? Why are they talking about this? Who are they to talk about such things? Retraice is about what's going on out there. It's a podcast. You already knew that. The short answer to that question is computer control. The long answer is nature, which is not effing around. Artificial intelligence, which is new. Natural intelligence, which is old. Strategic intelligence, by which we mean espionage, counterespionage, and covert action, which is in between new and old. And then there's humanity, which is the best part of what's going on out there. Retraice is for outsiders, but we came to the conclusion that outsiders are not players and the computer control game is player-oriented, so now we're learning to play. What do we mean by play? We're going to read a book? That's not playing. It is kind of playing. I love it. But it's just the beginning of the play. If you're a player in the computer control game, you are probably, let's see, if you're doing the actual AI, you are an artificial intelligence engineer. There are other players in the computer control game that are not going to be artificial intelligence engineers or are not already artificial intelligence engineers, but that's the position we're going to try and play. What do you think? Go for that one? I think go for that one. That sounds like a good one. Okay. Formal languages and pseudocode. So we've already talked about the other sections of AIMA4e. Basically, the body of the book breaks down into 6 sections, which we call, number 1, intelligence, number 2, problem solving, number 3, thinking, number 4, uncertainty, number 5, learning, and number 6, interacting. They have their own titles for those sections, but ours are better. Those are easier to remember. Yesterday we did the math appendix, which had 3 sections, basically the mathematics of problems and problem solving and complexity analysis and algorithm analysis. Then you've got section 2, which was linear algebra, or we could call that unknowns math. The mathematics of unknowns is that's the best I could come up with. I'm still working on my noun phrase for that one. And then finally, section 3 of yesterday's appendix was uncertainty math, the mathematics of probability. Okay, so formal languages, you should be thinking strings made up of symbols. Sometimes those strings can be infinite, then you need a grammar, then you're in the Chomsky hierarchy, and then, well, do you have a context-free grammar, or what sort of push automaton are you dealing with? And yeah, so a lot of sort of esoteric terms around languages and linguistics. We're going to be doing our definition, our grammar in Backus and Nauer form. I don't know who Backus and Nauer are, but they made us a way of a set of rules, 4 rules that we need in order to define our language or to define the grammar, specify the grammar of our language. What languages are we talking about? Are we speaking English? Yeah, well, that's one of them. That's the natural language, and you can definitely try and write English as in Backus Nauer form. I always want to say Backus Nori. I don't know why. I'm going to do that. Forgive me in advance. I'm going to say Backus Nori. I don't know why. Okay, but the languages that they define in the book include propositional logic. We've talked about propositional logic. It's a bunch of propositions, but it doesn't admit of what first-order logic admits of, which is objects and relations, which is a little bit more like the real world. The world is not filled with just propositions. It's mostly filled with stuff that's in relative position and other kinds of relationships to itself. So we need to be able Russell and Norvig and their team of co-authors need to be able to define propositional logic and first-order logic in terms of something, and that's a grammar, and then we write that grammar down in Backus-Nauer form. So what are the 4 components of a Backus-Nauer form grammar? The first thing you've got is terminals, which are the symbols or maybe the words that are like the base level of the language. So in English, they would be words, but they can just be a bunch of symbols. I'm not great at this. I'm not going to do a great job explaining the terminals. The other ones are easier. So just think words or symbols for now. Non-terminals that categorize the terminals. So the example they give is a noun phrase. Noun phrases like problems math or unknowns math or really all of my categories for the body, they're all single nouns, but the only one that I want to expand is section 2. I call it solving. But solving what? I mean, solving problems, right? But then solving, I just feel like a listener needs to know that we're solving problems and not puzzles, maybe, I don't know. But anyway, those are all nouns, but you could also call a noun phrase. But you can't call a noun phrase a noun, I think, if I'm remembering my English grammar correctly. Okay, so you need terminals, which are the basics, the words or the symbols that make up the formal language. And then you need non-terminals that categorize those words, like noun phrase or verb phrase or preposition or whatever. Then the next, so that's 1 and 2 components of Backus-Naur form. The third component is the start symbol, which is kind of, it takes some getting used to, but in English, the start symbol is sentence. In mathematics, it can be expression or XPR. EXPR is the example they give. And then in computing, it's program. There aren't strict rules about this. I mean, you can define a language using Backus-Naur form using whatever start symbol you want, but these are the conventions they're using here. And then finally, the interesting one, the rewrite, the last component of Backus-Naur form for a grammar for a language is rewrite rules. For example, a sentence can be rewritten as an expression and then an operator and then another expression, or just a new expression, or it can be rewritten as a number. You can have a lot of rewrite rules for English and maybe not so many for formal. English is not a formal language, it's a natural language. But formal languages like propositional logic, first order logic, can I come up with a third formal language? Well, I mean, programming languages can be written as formal languages in Backus-Naur form. I think there's nothing controversial about that, right? Okay, anyway, that's Backus-Naur form for using a grammar to define a formal language. I think, though, so this might seem a bit abstract, but let's bring it down a little bit more down to earth. I think in terms of compilers. Now, I'm not a compiler writer. I haven't written compilers, but I've sort of read into what it takes to write a compiler because they were mysterious to me. I'm like, what is happening when I write? Like, I have my code that's in my characters and on my screen, and then somehow it becomes computer behavior. Not all computing languages are compiled. Some they're interpreted, and I think there's another kind as well. But like virtual machine, is that compiled or interpreted? But anyway, it's the easiest way to think about programming languages that start from type. You write some code like a control structure like while this do this, and then somehow that becomes behavior inside the machine. Like the electrons and the voltages really change precisely according to what you told the computer, in quotes, the computer to do. A compiler is the best way to think about how that happens. A compiler is a program that takes an input language content in an input language and then puts it into an output language, converts it into content that's in an output language, and that ultimately that output language is voltage states on tiny little wires inside of a computer. And those voltage states, when combined with the architecture of your computer, will lead to the output. They constitute the input, and they will generate the output that you want. It's a bunch of little, on and off switches or light switches or however you want to think of it. It's really physically what it is voltages, and the way that you arrange the microelectronic components dictates or determines the behavior of your particular voltages in that computer. So source language to target language, you need syntax, which is the rules that govern how the input. I'm over my skis, people. I'm not really good in linguistics. Syntax is the rules for constructing meaningful strings or strings from symbols, and then semantics is extracting the meaning of the meaning from the syntactically correct string. For example, if you say in French, I will go to the store if it's not raining, the syntax of that is however you say that in French. Well, whatever the sound you would hear come out of a person's mouth speaking that correctly in French. The semantics of it is what I can translate into English by saying it in the English way that I just said it. So the semantics is what the French spoken string is, and the English spoken string have in common. I'm not a linguistics professor. Could you tell? I don't know. I didn't think you could tell, but I guess you can tell. So the semantics is also what a compiler has to do when it takes your high-level language like C or Python or whatever, and Python is interpreted and compiled, I think. It depends on what you're doing. You can use the Python interpreter. Or is it just no? It's just no. It's not compiled because you don't have binaries. And okay, but anyway, C or C++ or these other, Java is a virtual machine. Oh man, I'm out of my skis. Man, my skis. I got to learn to use these skis. But just stick with C or C++. These are compiled languages where you give it some source code, run the compiler. The output is a binary file, a file that's just ones and zeros. It's not ones and zeros. Okay, it's voltages in memory or in storage that gets put into memory and then connected via other behavior of your computer to the processing part of your computer and the registers and all this stuff. Why am I talking about registers? I need to stop. Okay, that's what I'm thinking about when I think about formal languages, and in particular compiling, like building a compiler. Or what a compiler does is, number one, syntax analysis. So you analyze the structure of the input language. Let's say French, or not French, but like C is a better example because you don't compile French, and then once you've done syntax analysis, which is like you tokenize and then you parse it to match it to the rules of the language that you're working with, then you go on to step 2 of a compiler. I'm getting all this not from AIMA, by the way. I'm getting it from Elements of Computing Systems, Neeson and Shokin. Great book. And there's a newer version than mine, but I'm working from the 2nd edition. I don't know, the blue one. The new one's black. After code, and then the second stage is code generation, where you do data translation and command translation. Because in computer programs, data and commands should be separated. Never the twain shall meet in theory in your code, but in practice, everybody puts not everybody, but it's easy to put data in your source code, which you shouldn't do. But it's too tempting. Okay. Compilers. Why? Okay, just this is the sort of stuff we're going to wrestle with. You're not going to learn Backus-Naur form until you actually use it for a while in the book. You're not going to care about it until you use it and it helps you. And I just think that people should understand that compilers are another place in computing where other than doing these high level artificial intelligence things. That formal languages are very important. Everything in computing is pertinent to formal languages, or vice versa. One last thing, I've mentioned a few times this Kernighan essay. Was it Kernighan? It was 25. No, Thompson. It wasn't Ritchie. It wasn't Kernighan. It was Thompson. His talk at the ACM. I think he was winning the Turing Award or something, I forget, on trusting trust. And it's like a 2 or 3 page talk, and it's about how you really can't trust computer programs. There's always a way to build a compiler that deceptively outputs something that has backdoors in it. And so when we talk about formal languages and compilers, we should also always be thinking in the long term, and even in the present term, how do you trust your compiler? Unless you write it yourself, is Thompson's point. If you can't trust code that you don't write yourself, or you can't trust code written by people you don't, unless you really trust those people. Okay, enough about formal languages and Backus-Naur form. The section B2, section 2 of the Appendix B, is just describing algorithms with pseudocode. When you start getting into actual programming, which I don't think it starts until chapter 2. In AIMA, you're going to see programs written in what almost looks like a programming language, but it's not a programming language. It's pseudocode. The reason they do this is so that the book's content isn't wedded to one particular programming language. You should be able to implement it in different programming languages, and also programming languages, especially Python, change so that you immediately date the book if you wrote it in Python. A few years ago, if you'd written it in Python 2, whatever, and then they go to Python 3, which is much different, and now there's no Python 4, but it's coming. So you write it in pseudocode, but you need to define what you mean by what in the pseudocode, and that's what they do. They give a list. They implement it on GitHub in Python and Java at least, and they probably do little things in other languages, but it's kind of a community project. And not everything in the Python is like fully implemented, but that's the one I work in. Okay, so what rules, or what do they talk about? Like, how do they describe their pseudocode? But basically, this is going to be like a list of reference points, so that like when you start reading the algorithms in pseudocode, you're going to think, oh, what does this mean again? Jump to the back of the book, whatever page it's on. 1031 is most of it, although it spills over on 1032. Jump to 1031 and just refresh your memory. What does the italics here, and okay, this, what is, yield, what does that mean again? And that sort of thing. So they talk about persistent variables. This is like a programming thing. Like there's this thing in programming where you can have, if you assign a value to a variable in a simple program, it's fine, but the more complicated your program gets, the more you have what's called side effects, where the value of that variable might change and you might forget or might not notice that you've changed the value of the variable, and then later in your code you think it should be one thing but it's actually another. The way you manage side effects, either you use a functional programming language where there are no side effects because variables are contained by functions. I haven't done any functional programming, so I think what I just said is true, but I know that functional programming is a solution to side effects. Global state, it's called global state, is another way of thinking of it. Like the global state of memory is the thing you don't want to constantly be changing or affecting. So you want to contain your variables inside something. The other way of doing it is object-oriented programming. That's the main way. That's most people have done object-oriented programming who have done any kind of programming. The value of the variable, unless you explicitly define it or assign it outside of an object, it's contained within the object. So there aren't side effects on variables. So anyway, so they do persistent, they use the word persistent to do this, and the way that they describe it is, and they say, agents use it for memory. So when they write an agent program, they're using, when they say persistent in their pseudocode, you should think of that as memory, and it can be implemented in object-oriented programming or functional programming languages. So that's persistent. Then you can take variables that have a certain italics, functions and are capital, I think. But variables can also be functions. So they give an example of what that looks like when you got a bit of overlap there. Indentation is significant. It scopes control structures, loops, and conditionals. If you don't know what this is, don't worry. You just have to do some programming and you'll understand it. But so like Python is the main language that uses indentation as significant. Most languages before Python don't use indentation. They use braces or something to scope control structures. They also do. I looked at this, like all the pseudocode today, and they also indent whole functions or the body of functions. So they use indentation for functions. They don't do it for objects because there aren't objects in their pseudocode. Their objects are part of persistent, which you can implement as objects, but you don't have to implement objects. So if you're an object-oriented programmer and you're looking for objects or classes or anything like that, you're not going to find it in the pseudocode, or even the equivalent of it, unless you consider persistent an equivalent to that. Okay, they explain destructuring assignment notation, default value, parameters, yield, which generates an element every time it's run through a loop. It generates a new element from a list of elements, or a sequence of elements, which can be a list. They explain their loops, their conventions for the different kinds of loops, and then lists, and then set notation, and then they say that arrays start at 1 instead of 0. In mathematics, you start at 1, and in programming, they tend to start at 0. Not all programming languages. So those are pseudocode conventions. None of that should stick in your mind. There's no way I could make it stick in your mind. It's pointless to even think too much about it other than to get familiar with the rules and know where to look them up on 1031 until you start actually interacting with the pseudocode and trying to write it yourself, or looking at the Python or Java implementation that they've done, that they make available on GitHub, and then trying to see how does this Python line up with this pseudocode. That's the real activity that will have you looking at 1031 like, what is that? Okay, yeah, okay. So yeah, that's it. Now, we've done all the categories of artificial intelligence theory and practice, 1 through 6. We've done the 2 appendices, the math appendix and the code appendix today. And I think, based on a suggestion from an internal suggestion here at Retraice, I think I'm going to try and sum it all up in a single segment tomorrow, because this is our 4th. Is this day 5 or 4? This is day 5. Yeah, it's Friday, so we started on Monday. It's still a lot to take in. It needs to, and I want to do it so like when we're done with AIMA, when we've mastered it, when we've done all the exercises, and there's nothing much more that this book can offer us, that day will come, and I want to be able to go back and say, okay, this was a 5-minute take on it from the high level point of view. Is that 5-minute take the same 5-minute take we would do after mastering the book? And you don't master the book. I don't want you to think that I'm trying to master. You don't master the book. The book is to help you master artificial intelligence. Although not artificial intelligence engineering, funnily enough. Artificial intelligence engineering is an afterthought in this book. Not an afterthought, but it's literally the second to last section of the book in the conclusion section, which is razor thin. But artificial intelligence engineering should be where we're going with this. If you're going to be a player in the computer control game and you're going to be writing AI code, you probably don't want to be doing research. I mean, research is huge and important, but very few people compared to the bulk of programmers are doing research code. Research code proves something's possible. It's the implementation, it's the engineering code that brings it into the world and makes it usable and makes it useful. You're going to be doing the engineering code. So AI engineering is what you want to be doing. But as of 2020, when they published AIMA4e, it's basically not a thing yet because it's still a new field, and you need lots of people have to work together and build the norms and improve tools and conventions and do a lot of discussion to make a discipline into an engineering, to bring engineering to a new discipline, a new science. Let's say if artificial intelligence is a science, I think it is. So we're going to be part of that. We have to do things other than learn the theory and the research level of practice. We're going to need to understand software engineering principles that already exist. But anyway, that's all down the line, or that's going to be woven into our study. But for our purposes tomorrow, we'll sum it all up in one go. That's it. All references will be on the website in the PDF notes, retraice.com. This has been segment number 61. Next segment's tomorrow, same time, 11 p.m. That'll be Saturday the 26th. Go Blue. Go Blue. Signing off.